I'd like to start our discussion about the acceleration caused by gravity with this picture. This picture is a time-lapse photograph of two objects being dropped from the same height. You can see up at the top, this part here that I'm mousing over right now, that's like a little trap door that has opened, so allowed these two objects to start falling at the same time. Feather, apple. And we can see from the picture, time-lapse photograph showing the position of these objects at equal intervals of time. So I asked the question on the side, what can be determined about the motion of these two objects? Hopefully, looking at this picture automatically brings to mind a picture that we've seen before. And that picture looks something like this, where we have the people shown at different places, worksheet that we looked at previously, where we looked at the concept of acceleration just in one dimension. These two pictures show exactly the same motion, acceleration, acceleration. In the picture on the right, it's acceleration in a horizontal dimension. In the picture on the left, it's acceleration in a vertical dimension. We can tell that because if we look at the pictures, right, the distances keep getting farther and farther apart as this object keeps going farther, farther, farther. That's showing us that that object is increasing in speed because it's covering a bigger displacement for each time interval. As far as what can we determine about the motion of those two objects, if we look, we could say first that this is accelerated motion because those intervals keep getting larger, larger, larger. Second, the velocity is the same for both of these objects because if we look at their displacements during equal time intervals, we see that those displacements are exactly the same. And then the third thing we should be able to tell about that is that the acceleration is the same for both objects because their velocities are changing by the same amount. Change in velocity, that's our definition of acceleration. What does this all mean? This leads us to our discussion about gravity. The reason why we start with those two pictures is because we have found out through extensive measurements, observations, and experiments that gravity will accelerate all objects at exactly the same rates. That's gravity anywhere in the universe, and that's any object, regardless of size, shape, color, what it's made out of, any of those things. Gravity will have the same effect, or at least the same acceleration, on all objects, and will cause them to accelerate at exactly the same rate. There's one gravity number that we're most concerned with, and that's the gravity that the mass of the Earth causes because it influences our life and our situation so very much. Gravity on Earth causes an acceleration of 9.81 meters per second squared. Or we also talked about the idea that we could write that as 9.81 meters per second, right? That's exactly the same thing as 9.81 meters per second squared. So, based on that, if we had to describe the motion of an object experiencing that acceleration, we'd have to say, because of our definition of an acceleration, right? Remember that our definition of acceleration is equal to, acceleration, sorry, not turning out the way that I wanted to. Acceleration is equal to delta V over delta T, right? The change in velocity over the change in time. An object experiencing an acceleration of 9.81 meters per second squared will have a change in velocity of 9.81 meters per second for every second that goes by. The velocity will change by 9.81 meters per second for every second that goes by. Because this number is so important to what we do here on Earth, and because it affects everything that we do, all the motion of all the objects here on Earth, and because it affects the motion of all those objects exactly the same, it gets its own special letter, and we refer to that as lowercase g. Anytime lowercase g shows up in a formula or a calculation, it's referencing this acceleration value, 9.81 meters per second squared. However, something to keep in mind. The gravity on Earth causes an acceleration of 9.81 meters per second squared. That doesn't mean that all objects will experience that much acceleration because that acceleration value only applies when gravity is the only force acting on an object, the only thing that's influencing its motion. We'll talk way more about forces in the next chapter, but for now, if gravity is the only thing influencing the motion of that object, then it will experience the acceleration of 9.81 meters per second squared. But if there's anything else influencing the motion of that object, air resistance, wind, somebody throwing it, somebody catching it, whatever, the acceleration will not be 9.81 meters per second squared. Could be more, could be less, depending on the other influences, but the 9.81 meters per second squared only applies to gravity. When gravity is the only thing acting on this object, we refer to that object as being in free fall, or sometimes we'll refer to it as weightless. Weightless is a term that we'll talk about more in the next chapter when we get to gravity, but for now, if an object is in free fall, it's experiencing 9.81 meters per second squared. Be careful. When you jump out of an airplane, parachuting, right, before you open up the parachute, you are technically not in free fall. Gravity is not the only object, or not the only thing that is influencing your motion. There's other things there. In order to illustrate this concept, we take a look at these two pictures. Earlier in the presentation, I showed you this slide that says gravity accelerates all objects at the same rate. And to show you that effect of gravity acting on all objects, accelerating them at the same rate, we show the guy on the moon dropping the feather and the hammer. We'll actually see a video about that in class. But here on Earth, we take these same two objects, right? Rock, feather, right? Drop them at the same time, we will not see that they have the same acceleration, even though we know that gravity causes the same acceleration. But remember, that same acceleration, gravity accelerates all objects at the same rate. But in a situation like the one on the right, where gravity isn't the only thing that's affecting the motion of those objects, we won't see that same acceleration for both. Actually, neither of these objects will see that acceleration of 9.81 meters per second squared because neither of them has only gravity affecting their motion. Air resistance will affect the motion of both of these. Obviously, the effect of air resistance on the feather is a lot greater than the effect of air resistance on this rock, but air resistance affects both of them. Because of that, neither one of these will have an acceleration of 9.81 meters per second squared, and neither one of them would be considered in free fall. Through observations and measurements, we've come to the realization that gravity here on Earth will cause an acceleration of 9.81 meters per second squared for all objects, regardless of their shape, their size, what they're made out of, whatever. Gravity in general will cause the same acceleration for objects regardless of where we are in the universe. The actual acceleration value, though, depends on location. So that leads me to this question here. What's the difference in these two motions? Most people look at these two pictures and there's really not much difference between the two of them. And there's a reason for that. Just to reiterate, right? Gravity causes an acceleration of 9.81 meters per second squared here on Earth. If you recall back from our previous lectures, previous ideas that we covered in the previous unit, acceleration can mean a bunch of things. Our definition of acceleration, right? A is equal to delta V over delta T. Any change in velocity is acceleration. So that could be speeding up and that could be slowing down. These two pictures, one of them is a time-lapse photograph of an object on its way up to the top of its motion. The other one is a time-lapse photograph of an object on the way down from the top of its motion. So let's make some connections to some things that we've already talked about. This motion, very similar to what we talked about previously in the lab with the acceleration on the incline, where we had the cart going up the hill. In this case, right, we'll use blue here, this was our reference point. We talked about the idea that the motion detector calls everything in front of it positive and everything behind it negative. As this cart is moving up the ramp, right, if it's moving in this direction, okay, its velocity is negative because it's in the negative direction. It's traveling in the negative direction based on our frame of reference. Positions are positive because it's on the positive side of the reference point, but the velocity is negative because it's traveling in the negative direction. But gravity is having an effect on this object. Now, gravity isn't pulling directly on this object, but this object is moving uphill, and that means that gravity is going to be pulling in this direction. That means that our acceleration being down the ramp caused by gravity is going to be in the positive direction. If we have a negative velocity and a positive acceleration, we talked about the idea that it's slowing down. Same thing over here with the ball. New frame of reference, we'll call this our 0 point. We'll call this the positive direction, and then that means down will be the negative direction. In this frame of reference, this object, if it's traveling upwards, is going to have a positive velocity. But gravity directed towards the center of the Earth, in this case, is in the downward direction, and we called that negative. If we have a positive velocity and a negative acceleration, once again, that means we slow down. All right? Doesn't matter that in this case velocity is positive, in this case velocity is negative. The important part being that the velocity, the direction in which that car is traveling, is in the opposite direction of which way gravity is pulling on it and causing the change in the velocity. Remember, gravity is causing the acceleration. Gravity is causing the change, and therefore it has to be in the direction that gravity is acting. This object is moving upwards, but gravity's pulling downwards, positive velocity, negative acceleration. Or you just flip the frame of reference around. Same concepts though. Just to reiterate, acceleration by gravity is always directed downwards. Technically, it's always directed towards Earth, or the center of the Earth, because that's where the gravity is coming from. Okay? If the object is moving upwards, acceleration and velocity are in different directions. This object is moving upwards, so it's moving, in the case of the frame of Earth we talked about, in the positive direction. Velocity is positive, but gravity is pulling it downwards. That makes its acceleration negative. Positive velocity, negative acceleration, slows down. Going back to a topic that we talked about earlier, okay, what does it mean that gravity is causing an acceleration of 9.81 meters per second squared? Let's say each of these photographs is taken at a 0.1 second interval. So if I take a look, right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pictures here. If this was taken at 0 seconds, the bottom picture was taken at 0 seconds, and the top picture, that means the top picture would have been taken at 1 second, right? 10 pictures, 0.1 second intervals, 1 second goes by. Knowing that gravity causes an acceleration of 9.81 meters per second squared, I can tell how fast this object is going in the very first picture. If I know up at the top of the motion, the velocity has to be 0, right? Because, as we've discussed, that object stops just for an instant, not very long, but it does stop. If 1 second has elapsed since this first picture down here, if gravity is causing an acceleration of 9.81 meters per second squared, that means the velocity has to change by 9.81 meters per second for every second that goes by. And that means that down here, this object must have been traveling at 9.81 meters per second when this first picture was taken. On the other side, down trip. Let's say we go back to the cart, right? If the cart's moving in the down the ramp direction, this still our reference point. This still the positive direction, this still the negative direction. If this cart is traveling down the ramp, its velocity is in the positive direction. It's getting farther and farther away from the reference point. We call down the ramp positive. It's moving in the positive direction. Gravity is still causing that acceleration. It's still pulling that object down the ramp. And that means that our acceleration is also positive. If we have a positive velocity and a positive acceleration, We talked about physically, that means that we're going to be speeding up. And that's what we see happening to this cart as it rolls down the ramp. It speeds up faster, 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 faster. The ball falling down from the top is exactly the same situation. Let's say we even change the frame of reference and we call the top of the motion the reference point. We'll still call up positive, we'll still call down negative. In this case, the ball is traveling in this direction, the downward direction. If that's the case, that means that the velocity has to be positive because it's traveling the same direction that we called velocity has to be negative in this case. Ball's traveling in the negative direction. Gravity is causing the acceleration. It's pulling the ball in this direction. That means that the acceleration is also negative. Negative velocity along with negative acceleration also means that object is speeding up. Think of it this way. If the acceleration is negative, that's causing the velocity to change in a negative fashion, or causing the velocity to become more negative. If the velocity is already negative because it's traveling in the negative direction, and acceleration being downwards is causing it to become more negative, a negative velocity with more negative acceleration means it's going to go faster in the negative direction. That's speeding up. To summarize, acceleration caused by gravity is always directed downwards, or like we said before, that acceleration caused by gravity is always directed towards Earth, which in this case is downwards. When an object moves downwards, the acceleration and the velocity are in the same direction. Doesn't matter if we call it positive or if we call it negative, they're still in the same direction. And that means we'll have velocity, acceleration, same sign. That results in an object speeding up. If we take a look before, or if we take a look at that same thing that we did before, right? If, once again, there are 10 time-lapse photographs, each 0.1 second intervals, that means it's going to take 1 second for this object to go from the top to the bottom. At the top of its motion, we've already established that the velocity has to be 0 meters per second. That means 1 second later, this object has to be traveling 9.81 meters per second. It just so happens to be in the negative direction. So its velocity will be negative 9.81 meters per second. Conceptually, if we look at the different speeds of the ball at equal intervals, quote-unquote time intervals from the top of the motion, we should see that the speed of that ball is the same, but the velocity is different because of the fact that velocity depends on direction. On the up trip, that object is slowing down. How much? Well, every second that goes by, its velocity decreases by 9.81 meters per second. On the down trip, gravity's causing the acceleration, so it's still going to change the velocity by 9.81 meters per second. It's just that on the down trip, it's making it go faster by 9.81 meters per second. So gravity causing the acceleration downwards, it always causes the same acceleration, 9.81 meters per second here on Earth, but depending on the motion of the object, that may cause an object to speed up, it may cause an object to slow down.